Hello. So we continue our discussion in combinatorics by talking about permutations today. Let me first define you what a permutation is. Any arrangement of a number of objects so that the order of the objects in the arrangement matters is called a permutation of the objects. Okay? So, for example, write down all permutations of the letters A, B, and C. How many permutations are there? Okay, so I want to write all possible arrangements of these three letters A, B, and C as my objects. Okay, so I can start with an A, yes, and then after that it will come a B, and after that it will come a C. This is one possible arrangement of these three objects, yes? But again, I can start with an A, but then I can follow it by a C, and then after that a B. So these are the only possibilities if I want to start with an A. I can also start with a B, yes, and then I can write A and C after that, and then I can again start with a B, but this time I follow it with a C, and then after that I follow that one with an A. And then I go and start with a C, and then I would say A and B, and then the other possibility is this. And I hope that you agree with me, there are no other possibilities. Each one of these items that you can see here is called a permutation of the letters A, B, and C. So in total, there are 1, 2, 3, 4, 5, 6 permutations of these three letters. Yes, so here, how many permutations are there? So I would say that the number of permutations is equal to 6 in this case. Now, let us go to the next example. The problem is more or less the same, but here I have repeated. I have two letters of A, one B and one C. Of course, the situation you need to be careful about that interchanging two A's doesn't result into a new permutation. Okay, so for example, you need to be a little bit organized so to make sure that you are not actually ignoring some possibilities. So let us start with two A's, and then I can write B and C. So for simplicity of writing, let us just ignore commas here, okay? And then I can have two A's again, but I can have C and B. So these are the possible ways of arranging if I start with two A's first. But I can write an A, and I put an empty space here and write A little bit later. But then I have two more empty spaces here and there. I have to fill them up with B and C. So I would write B, for example, here and C here, and then I will write something like this. This is also another possibility. Yes. Let me keep A here and here, and I want to have two empty spaces between A's. Then again, I can write B and C here, or I can write C and B here. So what's important is that in each one of these items you see that the order changes at least, because it is completely clear that I can recognize this one with any one of these that I have written here. So far I have succeeded to write 6 combinations, yes? But of course these are not the only possibilities. I can, for example, have two A's at the end, and then I can write B and C, then I can write C and B with two A's at the end. Or I can have A here and here, and then I can have B and C, then I can have C and B. Yes? But I can have two A's in between as well. So yes, for example, I can have two A's here, then I have B and C here, C and B there. And I hope that you agree with me, these are the only possibilities that I can write. Yes, So again, each one of these items is called a permutation of these objects A, B, and C, two A's and B and C. So A's are identical here. So even though A's are identical here, so it means that if I interchange these two, I cannot, if I just interchange these two, I cannot recognize the difference unless something else has changed so I can differentiate between two items. Okay, so then you count them 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So here the number of permutations is equal to 12. Of course, in this lesson we want to learn how to come up with this number without writing all possibilities and counting them. Is there any way that I can immediately answer these two numbers if I do not write all possibilities down first? And the answer is yes. Answering to this is actually quite simple. And answering this is also simple, but first we need to learn about permutation of objects in which none of these objects is repeated. So I have written a theorem here, number of permutations of distinct objects. Yes? And this content is clear. The number of permutations of n distinct objects is n factorial. Okay? And I hope that it is clear, it's easy for you to see why. For example, let us consider this case, this particular case. If I want to write a permutation of these three objects, I am facing a three-stage task. Yes? Writing a permutation of three objects is a three-stage task. So I can imagine that I want to fill up three positions. I can fill up the position 1, let us call it stage 1, stage 2, and stage 3. For stage 1, I have three options available. I can choose whatever I like among A, B, and C. So I have three, but I use one of them in stage 1, then I will have two of them left for me. Independent of my choice in the first stage, I have two options available, and for the third one, simply you can immediately realize that I have only one option available. So in total, I have 3 times 2 times 1 possibilities, which is a 3 factorial, and 3 factorial is actually 6, and that is the number coming. So in general, this is the simple proof for that. So if I want to give an highlight of the proof, yes, I don't want to spend time on that because that's exactly the same thing. If I want to write a permutation of n distinct objects, I am actually facing an n-stage task, yes? And then it means that I have n distinct positions. So for example, let me write it here. Position number 1 from the left, let me call it stage number 1, and then position number 2, I will call it stage number 2, and then I can continue position n minus 1, I will call it stage Sn minus 1, and finally the last stage, stage n, position number n. So in how many ways I can choose one item for the first position? I have n options, I have n distinct objects, so I can write n there. But now I use one of them. For the second stage, I will have n minus 1 options available, independent of the choice that I have made in the first stage. And then hopefully you can convince yourself that there are 2 options available, and finally there are 1 options. So it means that the answer would be n times n minus 1 up to times 2 times 1, which is simply n factorial. Yes? So this statement is also nice to know. Another way of expressing the above theorem is to say that there are n factorial ways to distribute n distinct marbles in n distinct boxes so that every box receives exactly 1 marble. So this is also very nice, comparing this problem with the problem that you have n distinct marbles. So for example, you can imagine n billiard balls, identical billiard balls, but they have been labeled with 1 up to n, and then you have n boxes labeled from 1 to n. You want to distribute these marbles inside these boxes so that every box receives exactly 1 marble. In how many ways? I can do that in factorial ways. Okay? Now let us go to this example and try to solve the problems using this theorem. Okay, so here, in how many ways can 6 people stand in a queue? Okay, so here people are playing the role of objects here, and needless to say, people are distinct objects, even though if they are twin, yes, identical twins, but they are distinct people. And then you know about queue. In queue, order matters actually. So I have 6 distinct objects. I want to arrange them in 6 distinct positions in a queue. So everything is actually according to this theorem. So it means the answer to this is simply 6 factorial, yes? And this is the answer. You don't need to explain more than that here unless you want to really know how much is that. And then what you do, you can just simply write 6 times 5 times up to 3 to 1, and this is 720. But I prefer to answer this as simply 6 factorial. Okay, we now go to the next example. Using the numbers 1, 2, 7, 8, and 9, how many 5-digit numbers with distinct digits one can construct? Can one construct? Yes. So I have 1, 2, 7, 8, and 9. How many objects you see? 1, 2, 3, 4, 5. Yes, they are distinct objects. And my goal is to write a 5-digit number. And everyone knows that in writing a number, order matters, yes? There is a difference between this number, 1, 2, 7, 8, 9. This is 12,789. If, for example, I interchange these two, this is a different number, 12,798. So needless to say, again, that the order matters here. I have 5 distinct objects and I have 5 distinct positions, yes, meaning the left-hand side of a 5-digit number, then digit next to it, etc., etc. So the answer is again simply 5 factorial. Yes? Now let us go to the next example. How many permutations, example number 5, how many permutations of the letters of the word table do start with T? Okay. And this is a standard in combinatorics. When I say in how many permutations of this, the letters of this word, I mean that I am going to use all the letters exactly the same number of repetitions that you see in the word itself. Of course, here you don't see any repetition of any letters here. Okay, so 1, 2, 3, 4, 5. I have 5 positions to arrange them. So for example, let me just give you positions here. So position number 1, if I want to write a permutation of the letters of the word table, I have to fill up 5 positions, 5 distinct positions. And why the order matters? Because they have asked about permutations. According to definition, I know that in a permutation order matters. Okay. But here I want to choose the possible permutations so that it starts with a T. So I don't have any problem here. So I put a T here. Then my duty is to fill up the rest of these positions. So, but how many positions you see? 4 distinct positions. And how many objects are left for me? So here T is already used, so I have 1, 2, 3, 4 objects, 4 distinct positions. So the answer is just simply 4 factorial. Yes? Okay, now let us go to the next problem. Example 6. How many permutations of the letters of the word nature do end with a vowel? Okay, so in the word nature, 1, 2, 3, 4, 5, 6, I'm facing 6 positions. I need 6 positions to write a permutation of the word nature. So I would say that, let me, for example, let's assume that this is position number 1. This is position number 1, sorry. This is position 1. This is position 2. Position 3, 4, 5, and 6. Okay, but there is a condition here. So I want to use these 6 letters, permutation of the letters. The order matters because of the word permutation. Do end with a vowel. Okay, so there are vowels here. So N, T, R. These are not actually vowels, but N, A, U, A, U, and E are vowels. So it means for the last position, I have 3 options available because I want to end the permutation with a vowel. Okay, so let me take this one, stage 1, filling up the right hand position. Okay, so how many options are there? Is 3. Okay, but let me call the rest of it stage 2. Stage 2 is filling up these positions. How many positions are there? 1, 2, 3, 4, and 5. Even though I can fill the first position in three possible ways, but I use only one of them. So assume that you used E. But then you will be left with 5 items and 5 distinct positions, and then it is 5 factorial. And this 5 factorial is independent of my choice for the first stage. If I have chosen U in the first stage, then I will be left still with 5 items, yes? So this becomes, stage 2 can be done in 5 factorial ways. Stage 1 can be done in 3 different ways. So this means that in total the question mark to this question is 3 times 5 factorial. Okay, so this is the answer to this problem. So I have 3 options to fill up the rightmost position, and after this stage is done, is completed, I am left with 4 distinct letters and I am left with 5 distinct letters and 5 distinct positions. In how many ways I can write the arrangement there? In 5 factorial ways. So by this product rule, the answer to the question is 3 times 5 factorial. Okay, let us go now to the next problem. Example number 6. Answer the following questions. In how many ways can 5 boys and 4 girls stand in a queue alternatingly? Okay, if just I ask you in how many ways they can stand in a queue, I would say that 5 boys and 4 girls means that I have 9 distinct objects, okay, and then it would be 9 factorial. But now I have this adverb at the end, so I want to arrange them alternatingly. But you see that the number of boys is 5 and the number of girls is 4. So I have 5 boys, distinct of course, so let me call them boy number 1, boy number 2, boy 3, boy 4, and boy 5. So this is first part of the problem. And then I have girls G1, G2, G3, and G4. So if I want to arrange them, they are 9 objects, and because they are going to stand on a queue, the order matters, and so it means that I have to have 9 distinct positions, yes? So let me make it quickly. Position number 1, position number 2, 3, 4, 5, 6, 7, 8, and 9. Yes? So let me number them. Position number 1 from the left, number 2, number 3, number 4, number 5, 6, 7, 8, and 9. Yes? Okay, is it possible to start with the girl? Let us see what happens. So assume that I put a girl here, and then I have to put a boy because I want to put them alternatingly. Then I have to put a girl, boy, and then girl. But there are no more than 4 girls, so there are 2 boys left that I have to put them at the end. But this actually this violate the condition, yes, because they should be arranged alternatingly. So this shows that I cannot start with the girl, I have to start with the boy. Okay, when I start with the boy, it means that these positions, this would be a boy position, these are underlined with blue, these are boy positions. And then these are underlined with green are girl positions, yes? So, I am facing a 2-stage task. I can define a task consisting of 2 stages for myself. I would say that the stage 1 is arranging the 5 boys on odd positions. Odd positions 1, 2, 3, 4, 5. They are 5 distinct positions labeled with distinct odd numbers, and I have 5 objects. So the first stage can be done in 5 factorial way. Assume that the stage 1 is done, meaning that assume that I arrange the boys in the odd positions. After this is done, I am left with even positions. There are 4 distinct positions labeled with distinct even numbers, and then I have I have 4 distinct objects. So the second stage can be done in 4 factorial way. Okay? Now this task is accomplished when both stages 1 and 2 are accomplished. Okay? So it means that I have to use the product rule. So the answer to the first part of the question is 5 factorial divided by 4 factorial. Yes? Now for the second one, so let me write this a little bit lower. Hopefully I can take it a little bit lower. Yes, good. So, and then let me copy and paste one of the versions for this to save some time. Okay, so let us go for the next stage of the problem. Okay, so the second part of the problem. So let me paste it here. So here I have only 4 boys in the second part of the problem. I have 4 boys and 4 girls. So it means that in total I will have 8 positions. So let me just clean the last position. So here I will have 4 boys and 4 girls. And I want to do the same problem. I want to arrange them in a queue so that they are standing alternatingly. But this time I have 2 options, yes? Either I can start with a boy, girl, girl, and boy and girl. This is possible. These are 4 boys and 4 girls sitting alternatingly, standing alternatingly. And the other way is that I start with a girl, G, B, G, B, G, B, G, and B. Again, the same story. I have 4 boys and 4 girls standing alternatingly. So here I have 2 options available. I can fill up. I can either fill up the even positions, the odd positions with boys, so it would be 4 factorial, and 4 even positions with girls, so it becomes 4 factorial times 4 factorial, or the other way around, 4 factorial for girls in the odd positions and 4 factorial for the boys in even positions. So the answer to this part would be 2 times 4 factorial times 4 factorial. So that would be the answer here. Okay? Okay, so here, but of course, if the difference between these two groups of people is more than one, so for example, assume that if I have 7 boys and 4 girls, it's not possible at all to arrange them alternatingly. Okay, now let us go to the next problem, problem number 8. There are 5 math, 6 physics, and 7 chemistry books. All the books, even the books on the same topic, are different. In how many ways can we arrange the books on a bookshelf? Okay, so this is very simple. So how many distinct objects do I have? I have 5 math books, 6 physics books, and 7 chemistry books. So it becomes in total 18, yes? I have 18 distinct objects, so the answer is just simply 18 factorial. But now, these are important ones. What if we want to have the books and the same subject next to each other? Okay, so how should we solve this problem here? Number 2. I would say that I have 5 math books, so let me call them M1, M2 up to M5. These are mathematics books. And then I have physics 1, physics 2 up to physics 6 physics books, and chemistry 1, chemistry 2 up to chemistry 7. But I want to arrange them in a way that all math books are next to each other, which is a more reasonable way of arranging books in a shelf, and all physics books next to each other and all chemistry books next to each other. So how can I solve that problem? So you can imagine it in this way. You can imagine that you put you can put math books in an invisible box. You can put physics books in an invisible box. You can put chemistry books in an invisible box. And now label, for example, the first one with capital PM, label the next box with capital P, and label the next one with capital C. So the first thing that I want to do, I want to arrange these boxes. I want to consider all possibilities of arranging these boxes. This is good. Why? Because if I move these boxes around, I am completely sure that the content of each box contains the same subjects. Okay? So the books with the same subjects are actually moving around together. Okay? So how many ways I can arrange M, P, and C? M, P, and C are 3 different objects. I want to arrange them in a row with 3 positions. So the first part I can do it in 3 factorial ways. This 3 factorial is coming from the fact that I have 3 factorial ways of arranging M, P, and C. But inside each one of these boxes, I can also have different arrangements of the books, yes? How many ways I can arrange the books within this box? 5 factorial, because they are 5 different objects. And how many ways I can do this here? 6 factorial. And how many ways I can do it here? 7 factorial. When this task is done, the task is done if all of these steps are accomplished. Namely, first I need to arrange these boxes, and this is not still finished because now I go inside the boxes and arrange every book inside each box. So it means that I have to multiply this by 5 factorial, multiply this by 6 factorials, and multiply this by 7 factorial. So this would be the answer to this part of the problem. Yes, and you realize that this notation of factorial is a very nice notation here. Otherwise, we have to write a very long list of products. Okay, so number 3. What if we want to have math books next to each other, but do not have any obligations regarding the books and the other subjects? Okay, so I think this is also clear. So this time, you have these books, Math 1, Math 2, up to Math 5. But then you have Physics 2 up to Physics 6, and then Chemistry 1, Chemistry 2 up to Chemistry 7. What you have to do, you have to put them inside a box. but you don't need to put any one of these inside any box. So you put it inside the box, and let me call it capital M. Then how many objects you see? I see a capital M, I see P1 up to P6, and I see C2 up to C1 up to C7. Let me just repeat this again. So here I just put a label M for this box, and then if I ask you how many objects, how many distinct objects you are facing, you would say that I have an object, capital M, and I have other objects P1, P6 up to C1, C7. So in total 6 objects here, 7 objects here, and 1 object here. So I will have 14 objects in total. So what I can do, I would write 14 factorial. Okay, 14 factorial gives me all possible ways of arranging these objects. But within these items, within this box, can also be arranged in 5 factorial ways, yes? So I multiply it by 5 factorial. So that would be the answer to this part of the problem. Okay, now let us go to the next problem. In how many permutations of the letters of the word talking are there exactly 2 letters between T and K? Yes? So, how many items are there? 1, 2, 3, 4, 5, 6, 7. So we have 7 letters. 2 of them are, of course, so how many positions I need for the permutation? 7 positions. So let me just draw something here. So the first position, second position, okay, so I have 7 distinct positions because I have 7 distinct letters here. But I want to arrange them in a way that it is guaranteed that between the letters T and K there are exactly 2 letters. So for example, I cannot put T here and K here because there is nothing in between them. I cannot put T here and K, for example, I cannot put K here because then it would be 3 items in between. So one possibility is to put T here, K here, T here, K here, because then I have exactly 2. Another possibility is to put K here, T here, then I will have also exactly 2 letters between T and K because it is not mentioned which one has to come first. So first, I would say that if you really want to do that, it means that you need to decide about the positions for T and K so that there would be exactly 2 empty spaces in between. Okay? So I would say that this position and that position can be taken for T and K because there are two spaces in between. Or I can choose this one and that one, the second possibility. There are still 2 in between, exactly 2 in between. Or I can choose these 2. Yes, this is the third possibility. And finally, I can choose these 2, and this is the 4th possibility. So I would say that there are 4 possible ways, 4 pairs that I can choose for locating T and K there. So assume that I have chosen one of these pairs. So for example, assume that you, for some reason, you chose this one and that one. Okay? Then there are 2 letters in between. There are 2 empty spaces in between. But now you want to fill them up with your letters T and K. If you want to fill up the left one, how many options you have? You have 2 options. Either you put T here, K there, or the other way around. So I multiply it by an extra 2 because I have 2 options how to put T and K in the chosen positions. Okay? Now assume that this is done in one way. For example, you assume that you put T here and you put K there. And what is left for you now? You have 1, 2, 3, 4, and 5 positions. how many letters, how many distinct objects are left for you? Yes, so you had 1, 2, 3, 4, 5, 6, 7 letters. You have already used 2 of them, so 5 is left for you. How many distinct positions you have? You have 5. 5 distinct objects, 5 distinct positions, so it becomes 5 factorial. And then you multiply all of them. Yes? I would prefer, of course, to write it as 8 times 5 factorial, and I will stop there. If I want to, I can calculate 5 factorial, 120, and multiply it by 8. Okay? So actually, I am breaking down this task into 3 stages. I choose a pair of positions with the property that I can have exactly 2 letters in between. After this stage is done, I take my letters T and K and locate them in the chosen positions, marked with this blue cross. And then after that, I will go and take my 5 left letters and arrange them in these 5 positions, 5 distinct positions. I can do it in 5 factorial ways. So according to the product rule, if I want to do them simultaneously so that the task is accomplished until the end, I have to multiply it. Okay, this is also another nice question. Example 10. In how many ways can 10 people stand in a queue if 2 of them do not want to be next to each other? Okay, so I have 10 distinct objects here, people. I want to arrange them in a queue, but 2 of them have some problems. They don't want to be next to each other. So how many ways I can do that? Yes, I will come to this kind of problems later. I will give you a very nice way of how to solve this problem if there are more than 2 people that, for example, don't want to be next to each other. But before that, this is simple for us to solve. 2 of them do not want to be next to each other. So do you remember, I want to use the complement rule. First of all, in how many ways I can arrange these people if I do not have any restrictions? Yes? So for example, let me call these people, person number 1, person number 2, person number 9, and person number 10. So assume that these 2 people have some problems. They don't want to be next to each other. So if I draw a Venn diagram for you here, assume that this rectangle represents all possible permutations of these people. Yes, all possible permutations. Yes, but all possible permutations, I partition them. I'm not saying that this picture is into scale. I'm just partitioning it into 2 parts. In some of these permutations, you will see that P9 and P10 are next to each other. So P9 and P10 are next to each other. Okay? In the other partition, so P9 is not next to P10. And then this is one thing very clear. It is not possible that I have a permutation that simultaneously satisfies this condition and that condition. If P9 and P10 are next to each other, they cannot simultaneously be not next to each other. And if they are not next to each other, they cannot be simultaneously next to each other. So this is important to understand because I want to use the complement rule and the sum rule. So you know that this plus this should be the all possible combinations. Okay, I know first of all the total number. I have 10 distinct objects. I want to arrange them, so the total number is 10 factorial. I can also calculate the permutations in which P9 and P10 are next to each other. Exactly like I have the physics books. Did you remember I put them in a packet? So here I can do the same thing. I can put them in a packet and move them around together. Yes, I can call it P. Then if I ask you how many objects you see one capital P with 8 other P's, it becomes 9 factorial. But of course, these people can be arranged in 2 different ways. So either you can multiply it by 2 or simply 2 factorial. So if I ask you what is this, you would say that this is the number of permutations in which P9 is next to P10. Yes? This is the number of all permutations. So by complement rule, if I subtract these two numbers, what is left for me is exactly this part. Exactly. Yes, so this is the answer to this problem. So sometimes complement rule is also comes into the game. So using this idea, complement rule, the product rule. So you see here, I have used the product rule to calculate this one. For each one of these, I use the theorem today, and here I am using the complement rule. So that's also one problem. Good to know about that. So remember this trick if you want to count the number of permutations in which 2 objects are not supposed to be next to each other. Try to solve it using the complement rule. As I told you, this problem becomes a little bit harder if I ask you if 3 people, none of them want to be next to each other. It becomes a little bit harder, but we will also design a method to understand this problem later. Okay, so now let us go to the next problem. In how many permutations of the word table does a vowel appear immediately after a T? Yes? So I think that this problem shouldn't be hard for you. Yes? So for the word table, 1, 2, 3, 4, 5. So I want to have 5 distinct positions. So 1, and then 2, 3, 4, and 5. Yes? So you need to interpret what's going on. So my goal is to write a permutation in which a vowel appears immediately after a T. Okay, so it means that, for example, T cannot appear here, because if T appears here, there is no position after a T for the vowel. Okay, so first you need to know where a position of T could be. T could be here. T can be here actually, or here, or here, or here, but not here. So I would say that how many options are available for me to locate T? 4 options for locating T. Now assume that I have chosen one of these for T. Okay, for example, say that you decided and put T here. Then this is reserved for a vowel. So how many vowels are there? 1 and 2. So then you have 2 options to fill up immediately the next position with a vowel. Yes. So this 2 is coming from the fact that this location can be filled with either A or E, but not of course both. You put one of them there. For example, assume that you decided for some reason to put E there. Okay, and now how many options are how many positions are left for you? There are 3 left positions. And how many letters are left for me? I have already used T and I have already used E, so I am 3 left. So how many ways I can arrange them? Simply as 3 factorial. So the answer would be 8 times 3 factorial. Simple as that. Okay. Let us go to the next example. There are 6 different shoe pairs. In how many ways can one distribute these shoes among 5 people so that each person receives a right-footed shoe and a left-footed shoe, and the remaining 2 shoes make up a shoe pair? Okay? I don't know how to make it clear. So, for example, let me write something like this. I have 6 different shoe pairs, so I would write it as left 1, right 1. This is assuming that this is a pair of shoes. L1 is the, so I think it would be better if I denote them with letter and capital letter and a small letter. So for example, assume that I write A and A. For a small letter, I'm assuming that this is the left-footed shoe and the capital letter is the right-footed shoe. And when you see the same letter, it means that that is actually a shoe pair. Okay? And then the next pair, let me write it B and B, C and C, D and D, E and E, and finally F and F. So I have 6 different shoe pairs. So for example, if I have A and B, it means that I have a pair of shoes. One of them is left-footed, the other one is right-footed, but of course this is not a pair of the same shoe. Yes? If I have, I don't know, if I have A, B, then it means that I have a pair of shoes. I have a pair actually of 2 different left-footed, so both of them are right-footed, but one of them is from this pair of shoes and the other one is from this pair of shoes. Yes? Okay, in how many ways? And then I have 5 people, so assume that you have 5 persons here. Person number 1, person 2, person 3, 4 and 5. So if here persons are the positions here. You want to distribute these single-footed shoes, yes, among these people. But what you want to do is that every person receives a left-footed and a right-footed shoe, and then one pair is left, but we want to have that pair a real shoe pair. For example, I want to have F at the end. I want to have E at the end. Okay? So how can I solve that problem? I would say that I decompose this task into different stages. The first stage, I would say that let me decide about the pair of shoe that I want to keep for the end. Okay? How many options are available? I can either choose this one or that pair, or up to this one. So I have 6 options available for the pair of shoes that is supposed to be left at the end. So it means that first of all, I take that pair of shoes and put it aside. For example, assume that you have decided to put this aside. Then how many 1, 2, 3, 4, 5 left-footed shoes are left for you, and 1, 2, 3, 4, 5 right-footed shoes is left for you. I want to distribute these things now to these people, but I cannot, for example, give this. I am not able to give this person A and B, because then it means that this person is receiving 2 right-footed shoes, which is not demanded in the problem. Okay, so what I say is that let me just concentrate on the left-footed shoes. How many of them are there? 5 of them are there. I want to arrange them in 5 positions in front of the people. Assume that you are keeping these people standing in a row, and then you will take these 5 left-footed shoes and you want to put them in front of these people. In how many ways you can do? You have 5 distinct positions and you have 5 distinct objects. So it is 5 factorial. Yes? And then multiply. After this is done, for example, assume that you decided to give this person the left A, and this one C, this one E, and this one F, and this one E. This one, what is left? B. This is one way of doing that. Then after this is done, you go and decide about the right-footed ones. And in how many ways you can arrange them here? Again, you have 5 distinct positions and 5 distinct objects, so you have another 5 factorial coming in. So this is the answer. But of course, here you know from your knowledge 6 times 5 factorial can be written as 6 factorial. So this becomes 6 factorial times 5 factorials, yes? So this is also the answer to this problem. And finally, the last example today, I want to talk about this. In how many permutations of the word mailbox are the letters A and M adjacent next to each other and the letters B and X not? Okay? So this you should be careful about. So this is like the arrangements that two objects, we don't want two objects be next to each other, but so you need to be a little bit more careful for this problem. So assume that, let me just draw a Venn diagram for you here. In this rectangle, I consider all permutations in which A and M are adjacent. So all permutations such that A and M are adjacent. Yes? These permutations can be viewed into two distinct groups. Yes? One of these, so one part of these partitions, so for example, let me call it here, a B is next to X, and in some of them B is not next to X. Okay? But you see that I am considering the whole possibility as not all the permutations, all the permutations in which A and M are adjacent. Among these permutations, I can divide these permutations in which A and M are adjacent into two groups. One group is that on top of this, that A and M are adjacent, B and X are also adjacent, and another group is that even though A and M are adjacent, but B and X are not. So what I am interested in? I am interested in this part. The number here, so let me call this one number M, this one number N. This is wanted. Okay? So if I ask you what is M plus N, you can answer that. So if I ask you what is M plus N, you can answer that. M plus N is the number of items in this rectangle. It means that is all permutations in which A and M are adjacent. So it is easy. So I want to put A and M adjacent. So I put them in an invisible box, for example. I have this MA, and then what is left for me? I, L, B, O, X. So let me check. I put M and A in a box, and then I, L, B, O, X, yes. So how many objects you see? 1, 2, 3, 4, 5, 6 objects. So it becomes 6 factorial. But multiplied, I can arrange these two letters in two different ways, because if I write AM, that's also acceptable because still they are adjacent. So I have to multiply it by 2 factorial. So if I ask you what is this number, you would say that this is the total number of items here. It's the total number of permutations in which A and M are adjacent. Okay, but then I want to go and calculate this one. So this one tells me that B is next to X. So it means that A and M are already next to each other. On top of that, we want to have B and X next to each other. So if I want to calculate N individually, so what can I do? I can say that N is the number of permutations of this word in which not only A and M are adjacent, but also B and X. So it means that I will put A and M in one box. I will put B and X in another box because they have to move around with each other. And then what is left for me? I, L, and O. In how many ways I can do this? One object, second object, third, fourth, and fifth object. So I will have 5 factorial, but I will have a 2 factorial because of this box, and I will have a 2 factorial for the other box, yes? So this is the total number n. Okay, so it is clear from this equation I want to find m, so m is the total number minus n. So this becomes 6 factorial times 2 factorial minus 5 factorial times 2 factorial times 2 factorial. And this cannot be simplified further in factorial form, so let us keep it in this way. But if you want, you can calculate that 6 factorial is 720, so it is 1440 minus 480. Yes? So how much with that? It's 960. So there are 960 permutations of the word mailbox, so that the letters A and M are adjacent, whereas the letters B and X not. Okay? Okay, so we will stop the lesson here at this point, and we will continue more interesting parts in the coming sessions. Okay, thank you and bye.